Okay.
Okay, thank you, Cheryl. Good afternoon, everyone. Welcome to the HAO Colloquium. Today, we are very glad to have Dr. Cha from MIT Haystack. So first, let me give a brief introduction about our speaker. And Dr. Cha is a research scientist at MIT Haystack Observatory. He earned his PhD degree in space physics from Peking University in 2012. He then worked at the Chinese Academy of Sciences and the University of Michigan, respectively. And he joined MIT Haystack Observatory in 2019. Dr. Cha's focus of research is the Earth's ionosphere and the thermosphere physics and the space weather. He has studied IT storm effects, multi-scale ionospheric plasma irregularities, and traveling ionospheric disturbances, or TIDs, ionospheric empirical modeling and data assimilation, subaurora and mid-latitude ionospheric dynamics through a combination ground-based and spaceborne observations. And today he will talk about 3D ionosphere imaging with a new TEC-based data assimilation system, or TDAS. So please take it away, Acha.
Thank you very much. Thank you for inviting me. So today I'm going to talking about TIDAS. So it's a TEC-based ionospheric data assimilation system. It's a regional, three-dimensional ionosphere imaging system that we aim to provide a high-resolution, three-dimensional electron density products. As you can see from the screen, that TIDAS has three different versions. So we have TIDAS over the continental US and TIDAS over the European region. And we also have TIDAS over the South America region. So today I'm going to talk about this regional data assimilation system. Can you see my outline? That's the second slide.
Yes.
Good. So first, I'm going to give a brief introduction of ionospheric data assimilation, then provide a description of TIDAS, three different versions, and followed by our space weather analysis by using TIDAS, and last one is the summary. So first one, I'm going to talk about the data assimilation. So why do we need to do data assimilation? Because we know the ionosphere is a very complicated dynamic system. So accurately imaging and modeling the ionosphere has always been a challenging task to the space weather community, because the ionosphere has not only very considerable climatology changes, but also significant weather fluctuations, both in time and space. So the data assimilation has been proved as an effective technique to specify the ionosphere, which is implemented by ingesting a wide variety of observations into background models via certain optimization schemes like the Kalman filter or variation approach, etc., etc. So ionospheric data assimilation systems, they can be classified on the basis of the background models. So some systems, they use theoretical background models, like the game developed by the Utah State University, and the game developed collectively by the JPL and the University of Southern California. So the theoretical background, they have the merit of providing a physics-based forecasting, so which is very good. Building upon that, some other systems, they do data assimilation by using the coupled ionosphere-thermosphere model or the coupled ionosphere-atmosphere model. For example, experts in NCAR HAO, I know that you do the TIE GCM DART data assimilation or the WACMAX DART data assimilation. And we know that in NOAA's WAPC, they have the WAM IPE data assimilation system. So the merits of using the coupled IT model is that we can utilize the thermosphere, because after the data assimilation, the thermosphere composition, they can have a relatively slower and long-lasting variation. So this will contribute to a longer timescale of the ionosphere prediction due to the self-consistent coupling mechanism between the ionosphere and the thermosphere, which is very useful. And there are also some systems that they use empirical background models, like the IDA 3D, IDA40, and the GIS, the IR10, the MIDAS, and other IRI-based global data simulation models, etc., etc. So empirical background models, they have the merit of low computation cost. So it's very efficient, but they are limited by their forecasting ability. So with all this progress in data simulation, there are also some needs. For example, we have the data needs that we have to incorporate more data sets, ground-based, spaceborne, from above, from below. And we also have the research to operation needs. Like we need to improve the nowcasting accuracy, we need to improve the forecast ability and the time lead with better uncertainty quantification. And last but not least, we have the science needs. Because most current data simulation systems that are built to run on a global scale with relatively close grid sizes. So that means they may not always have a best performance in specifying regional structures. So we have the science needs to develop regional data simulation systems so we can resolve some localized structures with higher spatial temporal resolution. So that's one of the motivation for us to develop TIDAS. And talking about regional data simulation products, we know that there are some operational services that they provide two-dimensional TEC results. Like in NOAA's WAPC, they have the US TEC, North American TEC, and GLOTEC. And there are also some products over other regions, like over the European sector, over the Australia, and over the East Asian sectors. So these are the operational products. They can provide quasi-real-time two-dimensional ionospheric TEC products. However, we know that the TEC is an integrated product. It can reflect the two-dimensional horizontal structures, but limited in representing the vertical structures. So we still have the science need to have a better specification of three-dimensional spatial distribution and the temporal variation of the electron densities. So our goal is to do a high-fidelity, high-resolution, three-dimensional electron density reconstruction for better retrospective studies. So that's another motivation for us to develop TIDAS. Okay. So with all these motivations, we have developed TIDAS data simulation systems. So I'm going to give a brief description. So the very first version of TIDAS was developed for continental US and adjacent regions. We do this for two reasons. So the first of all is due to the ample data coverage. There's very dense ground-based receivers over continental US. There are over 2,000 GNSS ground-based receivers. So ample data availability, that's the first reason. And the second reason is that we usually observe some large-scale ionospheric electron density gradients, the mid-latitude gradient structures. For example, the storm-enhanced density plume. So we need to better specify these gradient structures. So we developed TIDAS over this region. These are the data sets that we use to do the data simulation. So we have the line of sight slant TEC. So each line here represents a ray between the receiver and the satellite. The color represents the TEC unit. And we also use the cosmic radio occultation electron density profiles. And the JSON TEC, JSON altimeter TEC provides total electron content above the ocean surface. And last but not least, we have the Millstone Hill ISR measurement, provides the altitude resolved electron density measurements. So these are the data sets. And TIDAS ingest this data into the background NEQUIC model by using an ensemble 3D variation algorithm.
Hi, Chad, I have a question here.
Please.
Yeah, so there's different data sources for TEC. What are the essential differences? For example, I seem to recall that the JSON has a different altitude than the GPS TEC. Is that right? And
yes.
Considering the measuring points, will that have any influence on the results?
So the Jason TEC is the vertical TEC above the ocean surface all the way to 1,300 kilometers, while the ground-based TEC is all the way to the satellite altitudes. When we do the data simulation, we cut the region between 100 to 800 kilometers. So all those TEC, we calculate their proportion between this altitude region for us to do the data simulation.
Okay, thank you.
Okay, next we talk about the ensemble-based background error covariance. Because we know the background error covariance, that's one of the critical factors that directly influence the effects of the data simulation. In many prior studies, these error covariance, they are predetermined, which means they are stationary. They use some Gaussian-like functions, assume they are proportional to the ionospheric correlation. We assume they have Gaussian-like distribution. For example, here we show the two stationary ionospheric correlation. This is the horizontal correlation. This is an elliptical Gaussian distribution, and that's the vertical. So, but we know that in reality, the ionosphere is highly disturbed, especially during the space weather events. So they cannot always have this homogeneous isotropic performance. So that's why we need to use the ensemble method. So I think that's the standard procedure to do the simulation, like here in NCAR HAO. When you do data simulation, you also do the ensemble. You run the background model for 100 times, and you use the ensemble to calculate the background error covariance. So that's exactly the same procedure which I used here. After we do the background ensemble runs, we calculate these horizontal and vertical correlation. You can see they are anisotropic with some variations. So this provides a better specification of the background error covariance. And additionally, we use the three-dimensional variation approach, 3D VAR. It is a statistical optimization method that seeks to minimize a cost function that measures the closeness between the background and the measurement. To save time, I'm gonna skip the mathematical description so we can focus on talking about the data simulation results. So here is the data simulation results. So TIDAS can provide a three-dimensional high resolution, which is 1 degree by 1 degree, latitude, longitude, 20 kilometers in altitude, and 5 minutes, that's the time cadence, ionospheric electron density distribution. And here we provide some examples. That's the 2013 St. Patrick Day storm. That's the electron density distribution at different altitudes. So this horizontal maps. This is the vertical slices. So we can see the TIDAS can well represent multi-scale ionospheric density gradients. For example, the storm-enhanced density plume, the SED. So what is SED? We know that SED is a large-scale mid-latitude ionospheric electron density enhancement. They are usually observed in the local aftermoon sector during early stages of a geomagnetic storm. SED is typically characterized by a plume-like structure, like one can see from here. It's a spatially narrow channel with enhanced plasma density that's streaming sunward and poleward. So these plume-like SED structures can be well reconstructed by our TIDAS data simulation model. So before we talk more about the SED features, I want to show some validation of the TIDAS. So here we use the pre-excluded total electron content. That's an experiment for March 16 to 18, St. Patrick Day storm. So that's 16, 17, 18, 3 days. That's the TEC before a simulation. That's the TEC after the simulation. We can see it's significantly improved with unbiased, nearly the normal distribution with much narrow standard deviation, less than 1 TEC unit, sigma. And to the right panels, this is the electron density at the 300 kilometers. And we also show the cosmic the trajectory of the cosmic tangent points. So the right panel, they show the comparison of the profiles before the simulation, after the simulation. So we can see they provide an improvement of the profile specification. So that's validation of the data points. Now we can go back to discussion of the SED. I'm going to talk more about the science insights. Okay, so what science insights can TIDAS provide us? We can see these left panels. So these are the shaded contour of the F2 layer peak density, NMF2, so that's the color, and HMF2, that's the peak height of the F2 region, so that's the vertical axis. So they show the evolution of the HMF2 and NMF2 during the storm enhanced density plumes. So we usually describe the SED as a density enhancement. But TIDAS told us SED is not only a density enhancement, but also a layer uplift. We can see SED has a format of ridge-like structures. There is a considerable layer uplift, about 40 to 60 kilometers, higher than its equatorward and poleward counterparts. So we know SED not only an density enhancement, but also a height elevation. We can take a look at the right panels as well. So this is the electron density distribution as a function of universal time and altitude. So this is the Millstone Hill ISR measurement. So we have some data gaps. This is the zenith antenna and this fan-shaped electron density distribution that's measured by the steerable antenna, which can do the wide range azimuth scan. So in both pictures, we can see the signature of SED plume here and SED here. And the bottom two panels, they are the reconstruction given by TIDAS. So we can see they agree very well with the ISR measurement. They show the SED results. And one thing I want to mention that if we compare the SED on the storm day with the previous quiet day, we can see that the contribution of the electron density enhancement, they mostly occur above the F region peak height. Well, below the F region peak height, we can see the density is actually reduced. So the major contribution occur above the peak region. So that's another insight that the TIDAS provide us. So that means this TIDAS is a very powerful tool that can help us advance current understanding of ionospheric gradient structures. And we also need to know that we're not only talking about three-dimensional spatial variation, but we are also talking about the temporal dynamic variation, because the time cadence of TIDAS is 5 minutes. So actually, it can provide a four-dimensional spatial temporal variation of the gradient structures. So here is a movie. The upper left, that's the electron density at 300 kilometers. The bottom left, that's the HMF2 and NMF2 distribution. And the right panels, that's the TEC distribution. So we can see the dynamic variation of SED plume. That's ridge-like structures with electron density enhancement and the layer uplift. So this TIDAS can reconstruct the 3D morphology and the 1D temporal evolution of SED with fine-scale details. That's very powerful. So that's the very first version of TIDAS over the continental US. And after that, we did an upgrade. So TIDAS has been updated to incorporate the European region, because over the European region, we also have dense ground-based GPS receivers, around 900 receivers. And that's one reason. Another reason that the SED plume is multiple longitude features. Although we usually saw it over the North American sector, but it can actually occur over the European region and also over the Asian sectors. Here I show an example. So that's a February 27, 2023 storm. During the storm event, we here show a GNSS TEC polar view. That's the magnetic latitude, magnetic local time coordinates. This is the northern hemisphere. This is the southern hemisphere. So we see this SED occurred in multiple longitudes. It first occurred over the European sector. As we can see here, the SED plume occurred over the European sector. Then, with the rotation of the map, the North American sector going to the local noon, and we see the SED plume revived occurred here. And we can also see it in the southern hemisphere, the Antarctic region, although the data coverage is not so good. So over the European sector, the data coverage is a little bit less over Antarctica. But over the American region, we can see there are some data coverage. We can make a comparison between northern and southern hemisphere. So we can see the plume here, we can see plume over Antarctica. But the intensity is much less than the northern hemisphere. So that's another topic that's about interhemispheric asymmetry. So that's another topic beyond the scope. So what am I going to say that we saw the SED is multiple longitude features. It also occurred over the European sector. So this TIDAS European version, they can help us address the three-dimensional SED structures over there. So here I also show a animation. We can see the dynamic variation of the SED. So it's extended all the way from the mainland Europe, across the Scandinavia, across the British Isle, all the way to the Iceland region. So that's dynamic variation. And there is also some mesoscale structures. So that's regional data assimilation systems can provide us with these dynamic features. That's the second version of TIDAS over Europe. And last but not least, we developed a third TIDAS version over the South America. Because over the equatorial and the low latitude regions, we also have very large density gradients, especially the equatorial ionization anomaly. So we hope this TIDAS can help us address the 3D phenomenon over there. So this is the results over the South American sectors. These red dots, they are the GNSS receivers. And we also use Cosmic 2 radio occultation because Cosmic 2 mainly cover the equatorial and low latitude regions. So that's the line of sight TEC. This is the Cosmic 2 electron density profiles. And this is the JSON3 TEC above the ocean surface. And to the right, we can see that's a three-dimensional equatorial ionization anomaly. That's horizontal maps. This is the vertical slices. So we can see three-dimensional EIA structures. So the TIDAS results clearly show us that the EIA is a double peak structure near the F2 peak region, but gradually merged into a single peak structure in the topside ionosphere. So with TIDAS in hand, we can analyze the latitudinal difference, the altitudinal dependence, and even longitudinal variation of the 3D EIA. So that's one thing TIDAS can help us. Here I'm going to show another example. So this is a storm case over the South American sector, November 4th, 2021. That's a major storm. So the left panels, we show the electron density, HMF2 and NMF2, and total electron content. And the right panel will show the delta values. By doing delta values, we subtract acquired time reference. So we can see the storm-induced delta variations. So we can see over this period, there is a positive ionospheric storm phase over this region, then gradually eroded by the blue regions. Let's see it again. So it's about 30 to 50% increase of the electron density. And we can also see there's an elevation enhancement of the peak height. So that means the fountain effect is increased due to the penetration electric field. So that's one of the reasons to cause this positive ionospheric storm phase. Another reason is that over the equatorial and the low latitude regions, we have the increased O over N2 ratio. So that's composition effect. because the O/N2 ratio is increased over the equatorial region, equatorward of the composition disturbance zone. So that's why we saw that as the storm progressed, this positive storm phase was gradually eroded by this blue region. So that's equatorward movement of the composition disturbance zone. So this TIDAS results clearly demonstrate different drivers and factors in causing this ionospheric storm. So TIDAS can provide detailed and altitude resolved information to help us characterize the storm time ionosphere disturbances in three-dimensional domains. That's very helpful. So that's a third version of TIDAS over South America. Okay, any questions before I move on to the next topic?
Yeah, I do have one question. I think you probably briefly mentioned this, but I didn't fully get that. So when you develop the different models for these different geophysical regions, what are the essential difference except like the data source?
Yeah, they are actually not so much difference. The data source is different, but the method, the algorithm, they are the same. So I would call them actually the same model, but for different region. Predominantly, they are the same. Yeah.
Okay, thank you. We got 2 hands raised. I think Mihail first, and then John. Please unmute yourself.
Yes, thank you. You mentioned penetration electric fields. How do you calculate those? Where do they come from for your assimilation scheme?
Pardon, did you mention did you mean the electric field?
Yeah, where do you get them? Do you have measurements of the electric field? Is that what you're using? Or do you calculate penetration electric fields ahead of time?
Yeah, we do not have the electric field measurement. So here it's only we have implies or deduction from the electron density. That's because we only do electron density assimilation. We don't have the penetration, but we can deduce this information from the peak height variation. So the layer is elevated. So we assume that fountain effect is increased, but without actual measurement, we don't know the exact number of the electric field. So that's why we need more theoretical models like TiGCM to help us.
Well, there is a way to calculate the prompt penetration electric fields globally from solar wind data. So if you're interested, let me know and I will tell you exactly, because we are using that in the coupled thermosphere, ionosphere, plasmasphere electrodynamics model. And we do that on the fly, so it's real time. My other question is, you mentioned you are using an ensemble to get to the covariance. Do you do this versus time, or do you do it once and you assume that that covariance is valid for all times?
We do this ensemble for different times because our time cadence is 5 minutes. So for one whole day, we have 288 steps. So we do ensemble for each time step.
Okay, but do you, so if you have a storm, do you have to recalculate the covariance matrix is what my question actually.
Yes, for a storm that we calculate the covariance matrix for each 5-minute step. So it's very tedious job.
Yes, I know. Okay, one statement on your second slide, you said that WEM-IP has a DA system, a data assimilation scheme. That is not true. SWIPC does not have a data assimilation at all at this point. They are struggling to just tune WEM-IP based on some ionospheric, the global ionospheric data assimilation. But it's not a data assimilation. It's some sort of tuning.
Okay, thank you for the correction. I thought that's a real data simulation, but thank you for your pointing out. Yeah.
Okay,
My turn.
I think so.
Thank you. So I have a question, and I have to admit I had to come in and out. So if you've already discussed this, I apologize. But it sounds like, so for Cosmic 2 data, you're simulating electron density profiles and not TEC. Is that true?
Yes, we
Okay.
only assimilate the electron density profiles. Yeah.
Okay. And so, okay, then that sort of answers. So if you were going to assimilate TEC, line of sight TEC, would it have to be, would you use what kind of ray tracer model would you use for that forward operator? A straight line or a bent?
Okay, because for TEC, we are only doing the simulation over below the 800 kilometers. So we assume they are a straight line. That's for TEC. For Cosmic, because there are a lot of radial occultation, that means they are negative elevations. So that TEC are more low elevation, so they can easily go out of our region because this is not a global model. This is only a regional model. If we use the Cosmic TEC, it will go beyond our data simulation region. So it's really hard to calculate the mere part within this region. So because of that, we directly use the electron density profiles within this region. So that provides that's more easy to do a simulation. But for global data simulation, I think directly ingesting the TEC would be much better.
Yeah, thank you.
Gam first, and then Chen here also has a question.
Yeah, so I think this is just follow-on questions. So for the GNSS ground receiver, how do you deal with the ray tracing problem above 800 kilometers, your simulating box?
Yes, we use NEQuick to calculate a TEC from ground-based receiver all the way to the satellite height, and we make a comparison between the NEQuick and each TEC line, and we cut off the one above 800 kilometers. So that's an approximation.
Okay, so does the background like NEQuick or versus other background model, does that make a difference? How that affect your simulation results?
Yeah, that's the same one we use. Yeah.
I mean, does it sensitive to the whatever the background model you're choosing? Your method.
Yeah, because for now we're only using this single model. We haven't used other model as background, so I'm not sure about the sensitivity. But for ray tracing, we only consider the contribution below 800. I know there's a lot of contribution from the plasmasphere, but for this regional model, we have to exclude that part. So that means there are some deviation between our assimilated results and the actual condition because of the neglect of the plasmasphere.
Okay, all right, thanks.
Chen, please.
Yeah, you use both TEC from JSON and ground-based receivers. Are there discrepancies between these two TECs?
Pardon, can you say it again? You mean the difference between JSON and ground-based?
TEC, yes. Are there discrepancies?
Oh yeah, discrepancies. Okay, right. So right, for JSON TEC is there's a lot of noise, so we have to do smooth filter before we can use of the JSON TEC. But as you know that the JSON TEC, the data is very limited. It covers the ocean, only cover the ocean, and come back every couple hours. And we are doing 5 minutes time step data simulation. So the majority of the TEC information, it still came from the ground-based TEC, but there we do have some discrepancies. So previously we do a process to calculate the systematic difference. We remove that from the JSON TEC. If the level between JSON and ground-based, they have a difference, so we do a slight adjustment of the background level of the JSON.
Thank you.
Okay. Any more questions at this point? Oh, another one. Bill, please.
Hi there, nice talk. Do you have statistics on the post-fit RMS noise level of the TEC data, particularly the ground-based TEC and the JSON TEC? I'm curious about the noise level of those observations.
Not yet for statistical comparison, but I think I'm gonna list that as a future task.
Okay, thanks.
Okay, we can probably move on. You have one more session, and then we can still ask a question by the end.
Thank you. So next topic, I'm going to talk about some space weather analysis by using the TIDAS data simulation tool. So the first one is TIDAS can help us analyze the three-dimensional ionospheric variation during storms. So here I provide some examples. So that's three intense storms. So the first one is November 20, 2003. So that's the largest storm in solar cycle 23 with minimum SIMH reaching minus 490 nanotesla. So we can see the LCD structure here. And the middle one, that's the March 17, 2015. So that's St. Patrick's Day storm. That's the largest storm in solar cycle 24. And we also have the April 23, 2023. That's the largest storm in solar cycle 25 to date. So for each of these storms, the top panel, we can see that's the TEC measurement. So that's why we have some data gaps. So that's from Madrigal TEC. And the bottom one, that's the TIDAS reconstructed three-dimensional structures. So TIDAS can help us reconstruct the 3D ionospheric variations. We actually run TIDAS for over 100 intense geomagnetic storms. We're trying to find out which of them have SED. And we managed to extract about 49 storm events that has SED. And we are using TIDAS to do reconstruction, and we did a statistical analysis. So that's one of the current job we are doing. So for storm case, TIDAS can help us revealing the three-dimensional structures. So that's the first topic. And also previously, I talked some other storm events. But here I want to talk about another case, another topic that's about the solar eclipse. I think many people might still remember the 2017, the Great American Total Solar Eclipse. And maybe many of you have watched the April 8th solar eclipse 1 month ago. So we know the eclipse is an amazing astronomical phenomenon, but it's also a natural experiment that provides us an opportunity to analyze the ionospheric effects because of the sudden cutoff of the solar UV and photoionization. So there will be a local depletion of electron density in ionosphere. But we usually study the eclipse effect in ionosphere by using two-dimensional TEC results. So here we have TIDAS. We can analyze the three-dimensional variation. So that's an experiment for August 21, 2017 solar eclipse. So that's the delta NE variations at different altitudes. So we can see with respect to the progress of the totality path over the continental US, there is an electron density depletion, also passage. So the density depletion, they can reach 30 to 50%, and they can even exceed 50% over the F2 region. So they have maximum depletion between 200 and 300 kilometers. And the right panels, we show the delta TEC variation. So TEC showed 30 to 50% reduction. And this is the NMF2, the peak density. They also showed very large depletion during the solar eclipse. So that's an experiment for the 2017 solar eclipse. And we also did another experiment for the last year. There is annular solar eclipse. I believe many people in Boulder have saw this solar eclipse. It's October 14. And here we show some examples. These are the observations from the GNSS TEC. So these 4 panels, we can see the variation of the delta TEC by subtract acquired time reference. We can see it's about 15 to 25 TEC unit reduction. So it's about 30 to 45% decrease in total electron content. And we select 4 different ionar sound measurement because the ionar sound, they can also provide not only the peak parameters, but they can also provide the bottom side electron density profiles. So these are the electron density profiles measured by ionar sound. So these vertical lines, they mark the eclipse start, eclipse maximum, and eclipse ending times. So we can see there is a clear bite out of electron density. They occurred shortly after the eclipse start and reaching maximum about 30 to 40 minutes following the maximum obscuration, and gradually recovered after the eclipse end. So that's eclipse day, that's reference day. But one thing I want to note that these automatic ionosound measurement, they have sporadic data gaps, and they also have outliers. So we can only use the ionosound data to do a preliminary estimation of the decrease of the reduction level. But in order to provide a more detailed quantitative analysis of the reduction level, we are using our TIDAS model. So this is the TIDAS reconstructed electron density during the eclipse day. We can clearly see this bite out of electron density. So that's the reference day. By doing the subtraction, so that's the percentage variation due to the solar eclipse. So we can see very substantial electron density reduction of 30 to 50%, with the maximum depletion occurred near the F2 region peak height, between 250 and 350 kilometers. And we can also see this post-eclipse recovery. There is an altitude-dependent feature. With the lower altitudes, they exhibit a much faster recovery than the F2 region and the topside ionosphere. That's because the photoionization, the changes in the photoionization has a very immediate change to the photochemical equilibrium in the lower latitudes. So this altitudinal-dependent features can be indicated by our data simulation models. Okay, so this is my last slide, a summary that TIDAS is a new regional data simulation system for 3D ionosphere imaging, and TIDAS can provide a high-resolution, time-evolving 3D maps, and the resolution is as high as 1 degree by 1 degree, 20 kilometers, and 5 minutes. So TIDAS has 3 versions over US, European, and South American. And the TIDAS is a powerful tool for providing detailed altitude results information that can help us to advance current understanding of the ionosphere physics during space weather events, such as the magnetic storms and the solar eclipses. These are the reference list, and that's all my talk. Thank you very much.
Very juicy talk. Let's see. More questions in the room and online? Oh, Hali.
Oh yeah, hi Archa. Thanks for a great talk. I was wondering that the spatial dimension here said it's 1 degree by 1 degree. I thought that the ground-based network resolution can be higher, right? Is there a reason why you choose 1 degree? Can you go even higher than this?
Yes, for some particular region, it can be higher. For some region, it's lower. So this is like a balance.
Okay, I see. Another question is that because you do mention this is a 3D map, I was wondering in general for ionosphere structures, do you have like something like analogous to a baroclinic structure that is if you cut different altitude, that their horizontal structure is different from another altitude, or is pretty much similar at different altitude?
Yeah, there is a difference. I mean, the bottom side ionosphere, the F2 region, and the top side, there is an altitudinal difference. We are currently analyzing the solar eclipse event that occurred 1 month ago, and we're using TIDAS, and we found that there is a large altitudinal difference, especially at the top side ionosphere and the bottom side ionosphere. There is an altitudinal difference, and there is also a latitudinal difference. In the lower latitudes and higher latitudes, there are some different performance. So we're currently analyzing that result. But yes, the answer to this question is yes.
Okay, thanks.
Okay, Jen, you got another question?
Yeah, you mentioned that you saw the altitude raising of ionosphere altitudes in the CDs. Since most of your data are TEC data, where that altitude information come from? Mostly from cosmic profiles?
Okay, so I want to say for TEC, we use the slant TEC, the line of sight TEC. Okay, so it's different from the TiGCM DART simulating that you are using the vertical TEC. Here for slant TEC that can provide vertical informations. So any TEC above 25 elevation angle, we're using that. So because over American sector, there's over 2,000 GNSS receivers. This slant TEC can also provide the altitude, structures. But of course, the cosmic, they also provide the vertical information as well. So it's a combination.
Thank you.
Sorry, I just have a follow-up question about the resolution. You mentioned that there is some location you cannot get 1 degree times 1 degree. What's the requirement?
Right. For some region like above the desert or near the ocean, near the coast, we might not have that very dense TEC network. So, I mean, for that region, the actual performance might be lower than 1 degree by 1 degree. But for some region, we have very dense distribution, so that may increase our resolution to half degree by half degree. So in general, this is the compromise between different resolution. So we use a standard 1 degree by 1 degree, also because in magical data sets, our TEC products also has a 1 degree by 1 degree. So we want to make it consistent. But maybe in the future, for some key region of target, we can provide a higher resolution for very dedicated target region. But that's a future task.
Thanks.
Okay, next, Bill Larco.
Yes. Have you, or let's say, can you or have you seen density structure associated with subaraural polarization streams in Titus?
Yes. We saw some cases. There's a main trough, but during the SAPS event, the main trough is deepened and getting larger reduction that they are associated with the SAPS structures. So we are currently analyzing some events using coordinated like a millstone hill that provides some measurement of the velocity, and also use the DMSP. They also have some horizontal drift measurement. Yes.
Any surprises in the vertical density profile in the SAPS?
So far, we do not have surprising results. So that's why we are struggling.
Okay, thank you.
Thanks.
Yeah, I also have a related question, maybe too naive, but when you use the cosmic radio occultation data, I think you just mentioned that's basically a slant TEC, right?
For cosmic, we're using the electron density profiles, the retrieved profiles.
Okay, so in that case, then you're certainly considering both a 3D location.
Yes.
Okay, I saw that you just took like a slant TEC, but in that case, it may span like over a few degrees in latitude or longitude. But if you are using density profile, then it's different.
Yeah, for ground-based TEC, we are using the slant TEC because that elevation angle is positive. But for cosmic radio occultation means their negative elevation is going down. So in that case, it's really hard for us to calculate the portion between our regional grid sizes. So it's more easy to use the density profiles. But for global data simulation, I believe other colleagues, they just directly use the cosmic radio occultation TEC, the negative elevation TEC.
I see. Also, in the data source you have been using is mostly either TEC integrated or the electron density. So what do you think are the future direction to make use of like other variable, for example, the super down measurements of the convection or anything else that you think can be very well used by the assimilation tool?
Yeah, that's a very nice question because currently we are using an empirical background model and we are only do electron density data simulation. So that's why we only limited using focus on using TEC and electron density. But in the future direction, I think we can switch to a theoretical background like or SEMI3 or TIGCM. In that case, it provides us capability to ingest different kinds of observations, not only the TEC or electron density, the convection pattern, like from the superdawn, can also be ingested. So I think that's a future direction.
Okay, Chen, please.
I have another question. Why you pick a NE quick, not using the IRI model?
Yes, because it's quick.
It's a quick.
Okay, come on.
So, from your data assimilation system, what are the outputs? Do you have other outputs than density?
Yeah, we have a density NMF2 and HMF2. So yeah, basically it's density information.
Sorry, it's really nice to have you here. So that I'm glad to see a lot of discussion. But let me ask you one more question. So based on your experience with all of these data simulation studies, what do you think could be a guidance for future deployment of like more facilities, either on the ground or in space?
Yeah, I think that's a more strategic question. So in my level, I couldn't speak more about that, but I would lovely to see more all kinds of different data, no matter it's ground-based or space-based. But I think we need more stakeholder, more powerful person to make the decision. But I'm looking forward to more and more data sets.
Okay. Okay, one last round. Any more questions for our chat? If not, let's thank the speaker again. Thank you so much. Really nice talk.
Thank you very much.
Okay, thank